Till now we have seen the various cutting fluids in the previous classes. Now we have to study about their one of the important characteristics, that are rheological characteristics as well as thermal characteristics of these various cutting fluids. Among the cutting fluids that we have seen, we are most interested towards two cutting fluids. One is the mineral oil cutting fluid, another one is a bio cutting fluid. So the mineral oil plays a data where it is as a reference, and how we can improve in the bio cutting fluid, that we will see from the point of rheological characteristics, that is the flow and deformation science, as well as thermal characteristics. Till now what we have seen in the previous classes is advantage of eco-friendly cutting fluids and like vegetable oil based cutting fluid over the mineral oil based cutting fluids. We have also seen the machining performance comparison of vegetable oils cutting fluid versus the mineral oil. Okay, that means we have seen the performance of metal cutting from the point of biological cutting fluid, from the point of mineral oil also. How to improve performance of eco-friendly cutting fluids? Just in order to increase the performance of existing bio-cutting fluids. If the performance is approximately similar, as since we are working in this area and we have to improve. So the research somebody is taking up in this area, what they have to do, they have to continuously strive hard to improve the performance, improve the rheological performance, improve the thermal performance of that particular fluid. How to do that we will see. So overview of this lecture, we will see about the rheological characterization of cutting fluid. Coming to the first one, that is the introduction to rheology, various flows of the fluid, various rheological characterization and the measurement techniques, followed by the flow studies of cutting fluid, that is a concentric cylinder as well as a parallel plate and all those things we will see. Then activation energy and all those things we will see from the point of rheological characterization. Then we go to the thermal characterization of the cutting fluids, thermogravimetric analysis we will see, then followed by the thermal conductivity and followed by the specific heat of the emulsions. What is the emulsion and all those things you have seen it, but we will see what is the optimum emulsion for better thermal properties and all those things we will see. The rheological characterization of the fluids, rheological characterization is the most important, because if at all I want to study the flow properties of that one, because cutting fluid has to penetrate or it has to flow into the cutting region. So that is the main function. If it cannot flow nooks and corners of the complex machining region, it cannot extract. So the first and foremost thing that it should possess from the cutting fluid point of view is the rheological properties. It can enter, then the thermal properties can extract the heat that is generated in the machining zone. So that's why we have divided into two sectors. One is rheology, let it enter into the machining zone, then thermal properties, so that it can extract. That's why these two play a major role in the machining arena for cutting fluids. So introduction to rheology, as you all see the fluid flow in this particular picture, how the fluid is flowing and how the wave is taking place and all those things. These type of things, whenever you shake your glass with water and all those things, if it is a transparent glass and all those things, that you can also observe this one. At the same time, if you see the rheology, normally rheo means the flow, logos means the science, and the ology means the study. Basically the rheology is nothing but the science of flow and deformation. The science of flow and deformation is nothing but, for the fluids you are studying about the flow, for the solids or semi-solids you study about the deformation. For the semi-solids you can also study the flow properties. So that is nothing but the rheology. So if at all I want to see the flow characteristics as well as deformation characteristics of any particular fluids, whether it is a semi-solid or a liquid, one has to do the rheological characterization. If you see the rheology of the fluids, the fluid behaviors, normally it can be divided into two. One is Newtonian as well as non-Newtonian fluids. Newtonian fluid, normally it will have a proportionally increment with respect to shear rate. The shear stress will proportionally increase with shear rate, but it will not in terms of non-Newtonian fluids. The non-Newtonian fluids Most of the fluids are non-Newtonian fluids. That's why the non-Newtonian fluids again divided into two sectors, that is time dependent and time independent. In the time dependent, if you see again, there are two things, what is thixotropic and rheopeptic. In the time independent, again it will divide into two things, one is pseudoplastic as well as dilatant. Normally we study mostly about the time independent one, that is called shear thinning fluids, shear thickening fluids and all those things in the upcoming slides. So the rheology particularly about these cutting fluids helps in proper mixing as well as proper flow and deformation whenever the intricate complex regions of chip tool interface or workpiece flank surfaces comes into picture. So this is the beauty about the rheology. So introduction to rheology we are continuing. Normally if you see Sir Isaac Newton 1643 to 1727, so he published the scientific book called Principia, and where if you see in the 19th century scientists discovered the solids with liquid like responses and liquids with solid like responses. These are the changes that one can see. For example, if you see take the water, if you go to the freezing temperature, basically it will convert into solid. At the same time, the deformation characteristics of this, when it is solid, when it is a liquid, is completely different. That is what one want to say. At the same time, today the rheology is an integral part of the industry. Basically, if you take any industry like pharmaceutical industry or any other industry, it is, for example, if you see the plastics or paints, you have to spread the paint according to your wish. If the paint is not spreading as per your wish and it is delaminating, then there is no requirement. Or if you are facing a lot of problem, you take a brush and you just dip into the paint bucket and then you just put on the wall. Assume that it is very difficult because the energy required to paint on the wall is very high. That means that you don't prefer that type of thing. Why? Because you need better flowability on the wall. At the same time, it has to spread easily on the wall and your energy consumption should be very less. So you need to study the flow characteristics of this paint. For example, if you see the pharmaceutical industry, mostly the fairness creams, everybody want to become a beautiful person or something. So lot of creams are there. So whenever a person want to apply the cream on their face, what will happen? You have to apply it uniformly. The cream has to deform uniformly, it has to flow uniformly because it is a semi-solid. Normally it is a semi-solid complex suspensions. So it has to flow, deform and uniformly spread, and the look of particular person, whether it is a male or a female, doesn't matter, that it appearance should be beautiful or handsome. That's why always rheology play a major role in the pharmaceutical industry also. Like bio inks and inks also there. Nowadays people are talking about 3D printing. People talk about 3D bio printing. So you have to deform or you have to flow the ink along with the cells properly, otherwise you cannot make a complex surface. Similarly, the cutting fluids also are one type of these suspensions, because people nowadays are talking about nanofluids and other things. If you take the nanofluids, that is what you have seen in the previous classes, these are the cutting fluids or the emulsions with nanoparticles. Okay, so this also resembles similar to your paint or your pharmaceutical creams and all those things, but with low viscosity. That's why it is more important to study about the cutting fluids from the point of rheology. Categories of flow and deformation. There are two categories. One is Newtonian fluid and non-Newtonian fluid that we have seen already. The Newtonian fluid, the higher the viscosity of the liquid, the greater the force per unit area is required. That is, shear stress required is very high. That means you always should put the less energy as a customer. So if you see the non-Newtonian for the liquids, tau equal to n to gamma, or some people they say n Newton viscosity into gamma dot. So tau stands for shear stress, Eta stands for viscosity and gamma stands for shear rate. So, people also say that these are the gamma or gamma dot. Some of the books, if you are following about the basic rheology books, if you see there, some people give the gamma dot also. So, gamma or gamma dot, please consider as a shear rate. Shear rate indirectly means the full name for this one is shear strain rate. For the liquids, this is the equation which you may see in the fluid mechanics also. For the solids and other things, this is the equation. Shear stress is nothing but your E into E epsilon. So, since we are talking about the liquids, we are more worried about our cutting fluid. That is why we always think about the shear stress equal to the viscosity multiplied by the shear strain rate. It can be gamma or gamma dot. The Newtonian and not Newtonian fluid, as per the continuum mechanics is considered, the Newtonian fluid is a fluid in which the viscous stresses arising from its flow at every point are linearly proportional to its local strain. That means that the stresses are linearly proportional to the local strains. In the non-Newtonian fluid, it is not so. So, if the fluid is not following this Newtonian principle, if the fluids are not following the fluids which are not Newtonian fluids are all not Newtonian fluids. Most of the fluids follow the non-Newtonian behavior. We will see various flows. Since in the classification also we have seen it, the Newtonian is n equal to 1, which is, you can see this is the Newtonian fluid, and if the n is greater than 1, basically if you see here, we are plotting the shear rate versus shear stress. So, Newtonian fluid and non-Newtonian fluid, most of the things are non-Newtonian fluid. Apart from that, n all are non-Newtonian fluids. Non-Newtonian fluid, the first one is shear thickening fluid. That means, with respect to shear rate, the shear stress is gradually increasing. That what it means is, if the shear rate is increasing means, you will come across the rheometer, how the experiment is calculated or conducted and all those things are there. Assume that I have a parallel plate rheometer and we have a fixed plate at the bottom, the rotating plate at the top, in between you have a fluid. You gradually increase the rotation, you just give the rotation to the top plate. Okay. If the top plate rotating at very high speeds, that means as you time increases, if you are increasing the rotations, that means that shear rate is increasing. Just for analogy. So, if the shear rate is increasing, that means that your top plate is rotating faster and faster. So, you take the dilatant fluid, that is shear thickening fluid. As the shear rate increases, what is happening here is, it is becoming thicker. That means that stress required is increasing. That is called shear thickening fluid. If you see the other one, that is called shear thinning fluid, most of the fluids follow shear thinning fluid. So, shear thinning fluid or the pseudoplastic fluids, if the shear rate is increased with respect to time, or what will happen, the viscosity gradually decreases. That is what the shear thinning fluids. Thin means it is decreasing the viscosity or shear stress. Shear stress and shear rate are related to the viscosity. That is why sometimes I may speak shear stress, sometimes I may speak viscosity, both are approximately correlated. So, another one, if you see, that is called ideal Bingham plastic fluid, another one is non-Newtonian plastic fluids. Just if you see here, till up to certain stress, there is no change in the shear rate. That means this is called as tau naught, minimum shear stress. Later on it will act as a Newtonian fluid. For example, paste or a toothpaste, if you open the cap and you just put upright, what will happen? The paste won't come outside. For that purpose, if at all it has to come outside, you have to apply certain pressure with your fingers, then only it will come. That minimum stress that you are going to apply is your tau naught here. So, the paste is the ideal example or one of the examples for Bingham plastic fluid. So, that the flow starts. After applying certain pressure by putting your brush, just if you, what will happen, the flow starts like a Newtonian fluid. That is called Bingham plastic fluid, and good example is in the life, everyday life, what you are going to use is a paste. Non-Newtonian plastic fluids, if you put it, it is gradually increase. If you put more stress, what will happen? The flow will increase. That is about the non-Newtonian plastic fluid. So, from this one, we have seen the dominance of non-Newtonian fluids over the Newtonian fluids, because Newtonian fluid, common Newtonian fluid, all you know is a water, and the non-Newtonian fluids are mostly whatever available suspensions, liquids, honey, butter, these are all our non-Newtonian fluids. The viscosity is nothing but the resistance to flow of the cutting fluid. If you see here in this particular picture, the viscosity is low here and the viscosity is high here. For the same inclination or something, whatever is given, the flow rate that is falling from the test tube is gradually increasing from this to this. That is why the viscosity is gradually increasing. So, if you see here, the inclination is same, but the thing is that the fluid inside the test tubes is different. Okay. So, if you see here, the liquid is different. If you see second one, the liquid is different. As you move here, it is clearly you can see it is a semi-solid. Here the semi-solid, similar semi-solid is there, but deformation is there. Okay. So, the viscosity is increasing. If the viscosity is increasing, for example, from the cutting fluid itself, we can say the grease is one type of lubricant and the mineral oil is one type of lubricant. The mineral oil has a low viscosity, but the grease, whatever you use for your applications, that is nothing but high viscosity lubricant. So, viscosity characteristics, it changes with respect to temperature. Most of the cutting fluids will change with respect to temperature. As the temperature goes into the cutting fluid, what will happen? The molecules gain the energy, which is called the thermal energy, and it try to move apart. That is why always the cutting fluid fumes, whatever you have seen, which is going to the operator nose and all those things, these are because it gains energy and move apart, and distance between two molecules will gradually increase, and the force of attraction between those two molecules as the distance increases will goes down. That is why mostly the cutting fluids viscosity will decrease with respect to temperature. This cutting fluid significantly reduces when the temperature increases, that is what I said. So, the temperature as it increases, intermolecular distance of these molecules will increase. So, intermolecular force of attraction will decrease, that is why the liquid will become gas and it flows. Various methods to test the viscosity. So, simple test in the previous olden age or whenever the standard rheometers are not there, the people used to use Troll test, that is called just to take the viscosity of the high viscosity of the fluids thick, and they say low viscosity of the fluids as a thin fluids for the dispersions. Just they take a strip, the wooden strip or a metallic strip, and just they put into the liquid or semi-solid, and just they take out and they say depend on the visibility test, they can say that whether it is a thin or whether it is a thick fluid. But only thing you have to observe here is it is a qualitative statement. There is no quantity. Whether it is viscosity is X or Y, you cannot say. You can say only this is thick fluid, this is a thin fluid. You hope you understand what is the difference between a qualitative statement and a quantitative statement. The qualitative statement goes by like this, Ramu is a good boy, that is a qualitative statement. Ramu is 80% good boy is a quantitative statement. Okay. So, if you are quantifying by particular value, that is nothing but quantitative value. Here the people can say whether it is a thick or thin, but they cannot say the viscosity is this much or viscosity is this much, quantitative value they cannot say. The second one is finger test. Take this one and just move on or move apart both thumb and index finger. So, you can feel the trachea, which is nothing but the long, less trachea, then it is short. For example, paints and offset printing, inks and pigments, pastes, these are all done normally by the finger test in olden days. Nowadays, everything is used by the commercial rheometers to test the rheology, but these are the old tests. Okay. Again, this is also the qualitative statement only one can give. Okay. These people during our childhood, we might have also played with our bubble gum after chewing sometime just take like this and like this. So, but don't do that, people might have done. In fact, I have done it at childhood. Since our childhood, we don't have very good exposure to the bubble gums, or whenever we get, we used to make bubbles and all those things. But particularly from the health point of view, don't make the bubbles or don't put into your fingers and just expand. Then after that, you just put into your mouth and chew again. Don't do all these things, because bacteria or the microorganisms that are in the atmospheric conditions will easily stick on the bubble gum if it comes out. Like you just blow the bubble and it will blast, and again you take inside. So, organisms will come and it will go into your intestine and causes a lot of problems. So, that is the practical point of view, but from the course point of view, this you can do by the finger test. Anyhow, I want to convey that these two techniques are the qualitative techniques, but not quantitative techniques. The standard viscosity measurements, if you see, there are oscillation viscometry. These are the second versions, or the primary versions for the quantitative measurement. Vibrational viscometry, and there are called falling piston viscometry. This is the third one, and the fourth one is rotational viscometry, which nowadays mostly people uses it, the advanced version, and falling sphere viscometry. There are different types of there, and among these, rotational is very common. If you see the rotational viscometry or the standard viscometry, currently what we are using at our laboratory to test the rheological properties of the fluids is Anton-Par MCR 102, and we can also use Anton-Par series. That is, Anton-Par is a company which produces the rheometers. Just don't take in other way that I am advertising or something. There is a TA Instruments also produces these viscometers. So, many companies are there who produces this. For instance, what I am showing in this picture is Anton-Par rheometer. This is a schematic view of the rheometer. This one is a schematic view of the rheometer. This is the fixed bottom. This one is a fixed bottom 1, and this is the rotating plate 2, and in between there is a medium. This is called 3, and the bottom 1 having temperature increment or decrement options also, because some of the cutting fluids or some of the fluids that one want to check may be interested to check at higher temperatures also. So, for that purpose, there is a temperature increment and decrement options, and you give the rotation to the top plate by keeping the bottom plate constant. That is about the shear strain rate. If at all, as I already said, that my bottom plate is there, my top plate is there, in between I am having my sample. Not this, it has to cover the complete space of the top plate, because the top plate is smaller one compared to the bottom plate. That is why always it should occupy the circle, or if you go to concentric cylinders, it has to fill up to a certain point. What you do is, you just give rotation to the top plate, but bottom plate is fixed. That is about the rheology that you do. If you see this one, the second picture, shows the commercial rheometer. This is the head, that is a movable head, and this is the bottom. You can see here, but we are not using the same cutting fluid here to explain the rheometer or the rheology physics. We are using a semi-solid in this particular. So, this is the tool master, which is a small one, and this is the fixed bottom plate, and in between you have a sample. This is the sample. Okay. So, after you give the rotational speed to the top plate, that is this one, so that it will rotate, and this is the fixed bottom end will assist for keeping your sample. So, this is how the experiment will takes place, but this is for the semi solids and all those things. Normally you will use the parallel plate rheometer, but if at all somebody want to do the rheology of the liquids, normally parallel plate is not used. Whatever we have shown in this particular slide is to explain you how the physics of the rheometer goes on. That is what we want to say. For that purpose, easily understanding is by the parallel plate rheometer. Okay. The same thing we can extend to the concentric cylinders. In the current viscosity measure using rotational viscometers, whatever we have done at our laboratory for explaining you, the materials which we have taken in this particular conditions are two. One is biocutting fluid, another one is commercial mineral oils. As I said, this is a liquid or a liquid emulsion, because you have to mix with water and all those things. You cannot use the parallel plate rheometry because it may splash out when you give the shear rate and all those things. For that purpose, we have to move to some of the advanced tool masters, that is one of them is concentric cylinders. If you see here in this picture, you have a concentric cylinders where the cutting fluid is filled beyond the tool master. The tool master looks like this. This is the tool master, and you have a hollow at the bottom. So, just you go and put here, and so that it should cover completely, then you give the shear rate. That means that you give rotation to the tool master. So, you can calculate the viscosity. How the viscosity will be calculated? Normally, if you see the figure 1, this figure 1, what will happen? There will be a torsional sensor will be there on the top. Assume that you have given certain RPM, assume 15 RPM or 20 RPM, it has to rotate at that particular RPM at the air. Whenever you are putting a certain liquid in it, what will happen? It cannot rotate whatever the given RPM. For that purpose, it need, because it is resisted by the fluid's viscosity. For that, if at all I want to rotate at the given RPM, it has to put extra torque to rotate. That extra torque, it has an internal software to calculate, and it will give in terms of the viscosity, shear stress and all those things. That is how probably this type of rheometers are working. Shear stress, if you see the shear stress versus shear rate in for the mineral oil as well as biocutting fluid, the shear stress required for the biocutting fluid is higher compared to the shear stress required for the mineral oil based cutting fluids. Normally, it requires around 55 maybe, and this requires about 120 or something. Okay, 120 Pascal, and this is 55, around 55 Pascal. At 20 degrees, what it shows? It shows that biocutting fluid is much viscous compared to your mineral oil. Okay. So, in order to improve the viscosity, you have to play with respect to the water. Water is a Newtonian fluid. If you put it, what will happen? The viscosity will come down. So, how much water you have to put to make the emulsion? That you have to see and check with respect to thermal properties, and then you have to come back to the rheological properties. The striking balance between thermal properties and the rheological properties. From this particular point of view, the flowability of mineral oil is better compared to the biocutting fluid. However, if you see from the other point, the lubricating characteristics of the biocutting fluid is much better than this one, because the viscosity is very high, means the lubricating characteristics is very high, probably. The second one is shear rate versus shear stress at 100 degrees. So, at room temperature, or this is at room temperature or 20 degrees temperature approximately we are seeing. If you see both the fluids are following the Newtonian trend. Okay. So, what will happen, these cutting fluids, whenever it is exposed to the machining conditions, like with respect to shear rate, that means that shear stress versus shear rate at 100 degrees, it is not following the Newtonian trend, like gradual straight line increment, like the figure 1. It is not going like a straight line one, it is going like a non-Newtonian fluid, that is called shear thickening fluids, but at particular temperature. So, I am not talking about the temperature variation at this particular moment, but I am talking about the shear rate variation with respect to shear stress. The shear rate is increasing at 100 degrees temperature, the shear stress is gradually increasing, because at elevated temperatures, whatever the volatile things are gone and it increases its thickness, or it increases its thixotropy, it becomes some thicky liquids. That is why at higher temperatures the viscosity gradually increases, that means it follows the shear thickening fluids. As at 20 degrees temperature, you have seen in the previous slide that the linear proportional increment, that is why the viscosity is completely linear here for the both the fluids. So, the viscosity of BCF, that is biocutting fluid, is higher compared to the mineral oil cutting fluid. But if you see at elevated temperature, that is 100 degrees temperature, which is maybe a temperature that normally experience whenever the people are using like soft workpiece materials, there it is not a straight line, it follows a non-linear trend, and there also the biocutting fluid shows higher value compared to this one. That means that even at elevated temperatures, the lubricating properties of biocutting fluid is much better, but flowing characteristics are not up to the mark of the mineral oil. Now, we will see about the variation with respect to temperature. If you see the variation with respect to temperature, both the fluids are decreasing with respect to temperature. That means that whenever you are increasing the temperature, the particles in two particles intermolecular distance is going to increase with respect to temperature. That means that intermolecular force of attraction decreases. That is why the viscosity gradually decreases. If you see at 100 degrees or above 90 degrees, approximately both the fluids have approximately similar viscosity. Even if you have seen in the previous slides, the viscosity of the biocutting fluid is much higher at a room temperature, but the natural condition, that is that higher temperatures, which is in the machining region, both the fluids will have the same viscosity. That is the beauty about the biocutting fluid. That means its viscosity is decreasing, but if you see at room temperature, viscosity is very high. That means that the gradual change of viscosity is very high for the biocutting fluid. That means it will have better lubricating properties as well as better flowable properties. That is what I want to say from this particular slide. The viscosity index is an arbitrary measure of the change of viscosity with respect to the temperature. Okay. This we have to study, the change of viscosity with respect to temperature. What will happen if the viscosity index is very high? Normally, if you see the viscosity lower viscosity index, greater change of viscosity of the oil with respect to temperature and vice versa. Why I want to introduce this term is, if the viscosity index is higher, that means that it won't change much viscosity at higher temperatures also. If the viscosity index is lower, what will happen? The fluid will change its viscosity with respect to temperature. We will describe with respect to next one, that is called vapor pressure. This is the pressure exerted by the vapor in the thermodynamic equilibrium comes with respect to the condensed phases. That means, if I am sending a cutting fluid into the machining region, the cutting fluid has to penetrate into that region. At the same time, because of the temperature, it will change itself into the vapor, because intermolecular distance will increase because of gaining of the thermal energy. That is why it will convert into the vapor. Whenever it converts into the vapor, what will happen? It exerts the pressure. Assume that I have a chip like this and cutting tool like this. In between, my fluid jet will come. Okay, this is a fluid jet. If the fluid jet will come, what will happen? Vapor pressure kicks off, but it cannot kick down the cutting tool, but it has chances to lift up the chip, so that the new cutting fluid can penetrate into the region. At the same time, the viscosity index, what I am talking, if the viscosity index is lower, what will happen? The viscosity, it will change. If it will change easily, and this capillary action will be very easy. If the viscosity is low, what will happen? The cutting fluid can penetrate into the complex regions of the machining region. That is why vapor pressure it has to exert, and viscosity index should be lower. So, if you have seen the previous slide where the temperature variation, the viscosity with respect to temperature is high, for the viscosity change is very high for the BCF. That means that from this particular value to this particular value, it is coming. Okay, that means it has ability to easily exert certain pressure on the, in terms of machining region, exclusively on the chip. If you see the apparent activation energy of the cutting fluid, the relation between the activation energy and the viscosity are related by the Arrhenius equation, that is called mu equal to A into exponential of EA by RT, where A is a constant, R is the real gas constant, and T is the absolute temperature, and EA is nothing but activation energy. Whenever you take the log on both sides, you can convert like this. The apparent activation energy for the biocutting fluid is very high compared to the mineral oil. In that circumstances, the activation energy required to change is higher to the biocutting fluid compared to the mineral oil. That means that it won't change its form before mineral oil changes. That means that mineral oil has high tendency to change its low apparent activation energy, it will change, but biocutting fluid will have need more activation energy to change its form. That is what here I want to say. Now we move on to the thermal characterization. Here we will see the thermal conductivity and specific heat, about the emulsions and all those things. Thermogravimetric analysis of the cutting fluid. If you see, TGA is a method of thermal analysis which changes the physical and chemical properties of materials, measured the function of increasing with respect to temperature. Whenever you have certain cutting fluid, you just put this cutting fluid and change with respect to temperature and measure the mass, as well as you can also measure what are the gases that is evolving out. If you see here, with respect to temperature, the mineral oil started changing with respect to, as soon as the temperature is increasing, the red one is starting to change. But if you see the biocutting fluid, there is no change up to this particular portion. That means that it is still stable at that particular range of temperature, like up to 120, 130 degrees, there is no change. If you see the table column here, Up to 100 degrees there is no change in BCF, that is 0, and but the mineral oil has already consumed or it is gone about 11 to 13% or 9 to 13%. If you see up to 400 degrees temperature, what is happening? 79 plus or minus 3% is gone, but whereas other thing is maximum of 88% is gone. If you see 550 degrees, approximately both are same. That means the degradation with respect to temperature having better from the biocutting fluids compared to the mineral oil. So now we have to check which is having the good thermal properties. For that purpose, what we have done here is the emulsions are mixed from 2 to 20% of the, that is 1:2 to 1:20, the 1 liter of cutting fluid to the 2 liters of water, ranging from that to 1 liter of cutting fluid to 20 liters of cutting fluid. Now my major ambition for this particular slide is what amount of water that I can add to the cutting fluid is the question mark. For that purpose, we have used KD2 probe thermal properties analyzer, which will give the thermal conductivity of the cutting fluid as well as the specific heat. Thermal conductivity of the lubricants, normally mineral oil. If you see mineral oil, thermal conductivity of the mineral oil is 0.126, but the biocutting fluid is 0.151. However, water is very high. So now how much water one has to add for making the emulsion? With respect to the water increment, what will happen? Obviously the thermal conductivity will increase, because 0.6 is going to sit here on 0.15 or it is going to sit on 0.121, it is going to increase. That's why the thermal conductivity of the emulsion gradually increases, but it reaches to a optimum value at 1:8. After 1:8, the thermal conductivity of the cutting fluid is approximately same. So that means that from this particular experiment, one can say if you go for 1:8, you will have optimal thermal conductivity, plus since 1 liter of cutting fluid is mixing with 8 liters of water, compared to other one, assume that I am going to take 1:20, here 1:8, here 1:20, here the water content is very high, so the lubricant properties will be gradually decreases, but here lubricant properties will be much better. That's why from this particular graph you can choose the value based on your lubricating characteristics only, because the thermal conductivity characteristics are approximately similar in this region. Now whether we can choose 1:8 or whether we choose 1:20, that we will see from the point of specific heat. Now we will see the specific heat one. So specific heat of the lubricants, mineral oil is 1.2, biocutting fluid is again 1.467, that means approximately 1.5, but water will have higher, that is called 4.1 or 4.2 approximately. If you see this one, the specific heat will gradually increase irrespective of the mineral oil or the biocutting fluid with addition of the water. But after seeing 1:16, there is no much change in this region. So there is no much change. That means from the conductivity point of view, you can choose any value after 8. From this particular point, you can choose 1:16 to have the specific heat, volumetric specific heat will be better at 1:16. So 1:8 is good, after 1:88 is good. So if you choose 1:16, you will have the thermal conductivity properties better, because you have seen 1:8, beyond 1:8 it is good. If you choose 1:8, what will happen? You will have this much volumetric specific heat. If you choose 1:16, this much volumetric specific heat. That means that If you are going beyond this one, what will happen? You are not gaining much, but the thing is that lubricating characteristics will lose because your water content is going to increase. So optimum conclusion from these two thermal characterizations is, if you go for 1:16, you will have better thermal conductivity as well as volumetric specific heat. Anyhow, with respect to mineral oil, these values are much higher compared to your mineral oil. Okay. Summary: today we have seen the rheological characterization of the cutting fluid, which is introduction to rheology, various fluid flows and the various equipments that are used, the flow studies of the cutting fluid using concentric cylinders, where we have studied of the basics about the parallel plate rheometry. However, the application of the cutting fluids which we have seen is from the concentric cylinders. Then we have studied the activation energy of the cutting fluid. Then we proceeded for the thermal characterization, where we have seen the thermogravimetric analysis, that is percentage of mass change, then thermal conductivity, and followed by specific heat of the emulsions. And from this study, the emulsion composition is better if a person can choose in between 8 to 10. If at all you are choosing common mineral oils that is available and biocutting fluids. So the bottom line one can take up from this particular, for the research point of view, is that they can choose between 8 to 10 or 12 liters of water you can mix with respect to the 1 liter of your cutting fluid, and you can perform, because that is the best range that is given from the thermal conductivity point of view, as well as you should mix as minimum as possible for the highest thermal conductivity, so that the lubricating property of your mineral oil will be remain in a good condition. Okay, that is about from the research point of view. From the BTech people point of view, it is, as I said, books it is not available. Please go through the slides and follow the slides. That's about today's class. Thank you.